cloud systems, we need to wait until we have engineered the water thing out there. Yes, welcome to the Monday afternoon session. My name is Norbert Ritter. First, I want to apologize that I look a little bit like having had a failed plastic surgery. But it's not. I just fell over. Right before my flight.
Yesterday night, huh?
You see, you're surrounded by friends.
These remarks are not unexpected. So, yes, it's my pleasure to. I think that will not prevent me from being happy to host the session. So, and the session is about cloud and stream processing. And we will start with a presentation given by Steffen Becker from the University of Stuttgart. He's representing the area of reliable software systems, and he's going to be talking about actually engineering scalable cloud systems. He does that from a software technology point of view. So please.
Okay, thank you for the introduction, and welcome everybody for my talk. It's a talk about the CloudScale project. The CloudScale project was an EU-funded FP7 project, which lasted until late 2015, and then we continued to work on it for, let's say, 1.5 years in writing a book about it. And still today we are extending the results from the project even further. So it's in a sense an ongoing thing, but the presentation here is reporting about the stuff which has been done and which was finalized in the end. Yeah, I mean it's a SummerSOC about service-oriented computing, so I think I don't need to introduce that much cloud computing. But when I initially created the slide deck, I had some nice metaphors for the important parts I'm talking about here, and that's basically the focus on resources. I mean the title of the talk says it already that I'm talking about scalable cloud systems, and the project was called Cloud Scale, yeah, so the emphasis is on scale instead of on cloud. The question was, okay, how can we engineer systems in the cloud that fulfill their expected quality properties? Yeah? So the focus is on quality, as also my department says, so reliable software systems is all about software quality. And then I said, okay, the metaphor could be something like cars driving on roads. Yeah? So the road is a resource, the car is a request. The car wants to go from one point, the source, to its destination. That's probably the kind of the metaphor for the work the car wants to do. Yeah? And the sum of all the cars on a dedicated piece of the road, that's basically making up the load of that piece of the road. Yeah? And the overall load on a piece of a road is basically a sum of all the work being done by all the cars, which is in the car setting at least not so much regulated, but in the IT system world also often not so much predictable as we would like it to have. Yeah? So in a good situation it looks like this. We have resources, 3 lanes, cars running on it, and everything runs smoothly. Yeah? So they are obviously the amount of resources match the amount of work and load. That's not always the case. That's a picture taken from the Ruhr area where my wife comes from. That's a situation which you often experience when you drive there. You have a red light which indicates that you're not allowed to drive on the road because the road is occupied, and that's basically a mean to regulate the load. Yeah? So you're not allowing so much cars on a piece of the street, and that gives you some back pressure. It's also pay per use, at least in some countries, yeah, which is a similarity to cloud computing as well. The resources are available, we just need to order them, and usually we have the impression that we can order unlimited amounts of those resources at any time, and when we are done with them, we release the resource again, and then we stop paying them. But sometimes it's also the case that we have a problem. That's where limited processing takes place, so the amount of resources is actually not enough to match the demand, and then we see congestion. So that's a picture taken from my home area, so to say, Frankfurt. It happens frequently there that the amount of resources do not match the demand, and then we see a delay in the processing. And okay, now you could argue, okay, but that's a bad situation, so that should not happen in the cloud system where we have unlimited resources. But sadly, also there, it can easily happen that the amount of resources we have are running out, because this unlimitedness is just...
Sorry, not unlimited, but unbounded.
Okay, but even that is not true in reality, right?
Okay, but it's always finite. It's only unbounded for the user. The user doesn't see the limit.
Yeah, and the problem is also often that some resources are also just unlimited or unbounded, but some others are not, and therefore we still see these kind of congestions. And then when the capacity is exceeded, so that's basically now the bound. Yeah, so when we reach the bound, that's what we call the capacity in the project. Then obviously we can't do anything anymore, because then even increasing the number of resources is not an option anymore. And this bound can be also again of different reasons in reality. I mean, it might be even that resources are still available, but our budget ran out. Yeah? So if we are not having any more money to pay more resources, then also it's a bound for our system. One of the fancy features is that we have elasticity. So elasticity is a result of the fact that the resources are not pre-allocated, but we can allocate them at runtime, and we can change that at runtime. And again, a picture from Frankfurt area, where this is also done frequently with the cars, where the roads are dedicated for the inbound and outbound traffic differently, whether it's morning or in the evening. So in the morning we have more capacity going towards Frankfurt, and in the evening you have more capacity going out of Frankfurt, which is some kind of elasticity. I mean, in a limited fashion, but basically as a metaphor, it works the same in the IT system too. So we increase the amount of one or more resources or resource types, and then we get better processing. That's at least the hope we have, or the idea we have. There's also legacy systems. Legacy systems cause a lot of problems, also for our cars. Yeah, so if you need to run through this with the load according to the one we saw on the previous slides, then obviously that's not going to work. The cars will get stuck. I mean, if you're often here, you can only drive through with special cars, I would say. So even the size of the car might be limited. And in reality, also those legacy systems, they cause quite a lot of problems when we want to migrate them to the cloud, in particular when we want to migrate them in a way that they take advantage of this scalable infrastructure or the elasticity. Because then we need to resolve all those limits we saw on the previous slides in those legacy systems, and that means we need to first of all be aware of them, which is not often the case. Yeah, and then we need to do modernization if we find some bottlenecks, and modernization, as again with the streets, so again here the metaphor is pretty good actually, it takes a while. Yeah? So modernization is on a completely different time scale than actually taking advantage of elasticity and things like that, because usually you have to take the code, you have to rewrite the system, and as we learned yesterday in one of the doctoral symposium talks, rewriting seems to be the major task in that situation, and that can take even years if you're in a bad situation. Now, one thing the road planners do, which in IT probably most of the people are not doing that much, is they do more upfront planning and simulation of the endeavors they plan. So if your question is which of the roads are the most congested ones, where should we build new roads to increase the overall throughput of the total system, then in street engineering, people use a project like this one. So this is Sumo for those who know it. It's a traffic simulator where you can basically describe where the cars are going from which point to which other point in which load situation, and then you can make statements about where to either modernize or build new streets. Yeah? Now the question is, okay, what happens if we look in our domain, the cloud domain, I mean software engineering domain in this case. So one of the typical tasks we might see, that was a task we had also as a demonstrator in the project. We have a 15-year-old JSP written web shop. As you see, it's not anymore the most modern software system. We need to modernize it, and now we were imagining, okay, we are running that system, it's a bookshop, and finally we have some success. More users are coming, so that means more load is put on the system, and we want to engineer now the system in a way that it fulfills these requirements. So people today would suggest, okay, let's take this system and modernize it in the most fanciest hype word. I just exchanged it yesterday from 3-tier cloud system into microservices system. That's basically probably what most people would suggest today. So cutting it down into smaller pieces where each piece fulfills a function and scales independent of the other one. So I mean, the scalability is again my focus in this setting. And that's basically the part where this step from not only cutting down the functionality in smaller pieces, but also putting them in the cloud and making them elastic is an important task. And now if we have an engineer in software engineering, he might come up with these questions, okay, but will it scale now? I mean, the answer, if you just take an arbitrary legacy system like the one we had there, and you put it into the cloud, then, okay, nothing happens. It runs as bad as before. So it doesn't make use of additional unbound, unlimited resources because it simply wasn't designed for that. And I mean, it's so that's not a problem, but it doesn't care for the new situation. The question is, okay, up to which situations would it run? So what's the maximum work and or load the system is able to cope with? And if it's not the one we want, so if the load or work is not sufficient for the situation we're planning, what can we do? So where are the problems in my application?
But again, if you ignore data consistency problem, even the worst application will scale if you put auto-scaling on.
Exactly.
Data consistency problem.
Yeah.
Okay.
Depends. I mean, also the best database has its scalability.
You can sell even more books because you somehow replicate.
Absolutely.
Yeah, exactly. I mean, that's the. I mean, as I said, if you replicate the database and you don't have consistency among the databases,
That's the problem.
then everything is fine, but that would break the functionality of the system, right?
Yeah.
That's why you have Spanner.
Absolutely.
Oh.
Yes.
Dynamo.
Yeah, absolutely.
Okay, so the remaining of the talk, and in between I will always switch a little bit to my tools and give you an idea how they look like. It's like this, so I will give you a short introduction in this example I had. We'll show you, that's the main part now, for the rest, the cloud scale tools we developed and what we were able to do, and then summarize the talk and probably have some time for questions. If you are interested, everything is now written down in this book and available for read-up. So there's also much more details in the book than in the talk, so if you're interested, you can have a look there. So cloud computing, the most important, and I mean, I hope that all of you know that this definition, the most important property I'm focusing on here is one of the rapid elasticity. So I want to build an application which makes use of rapid elasticity, but I want to engineer it. And engineering it means in the way the traffic planners did engineering with Sumo, so I want to upfront analyze the system, simulate the system in a way that I can make statements about the system's behavior, and ideally without implementing the system, because implementation takes a lot of effort. So we want to replace the implementation effort with modeling effort, which is also often not so little as we hope. But in general, it's much less than the actual implementation, and then we want to make statements about the fulfillment of the requirements, in particular the elasticity and scalability requirements. So in our motivation example, if you want to refine it a little bit more, so we have this online bookshop, we have the customer who uses it, and then now we have some more elasticity scenarios. I mean, that's the first thing you need to probably consider in your software engineering endeavor is what are the elasticity requirements and how to write them down. I mean, there's different ways of doing that. We saw also some of them yesterday with user stories or non-functional quality property requirements and so on. There's not so much standards, at least not ones I'm aware of, for writing down elasticity requirements. And there's also not so much metrics at the moment for evaluating the elasticity of the resulting system. So even systematically testing elasticity is not so easy these days. We have our manager who wants to have the new system, and he wants basically a running shop where where he would like to have an ideal curve like this. So this curve shows on the x-axis the number of consumers, and on the y-axis it shows the operational cost. So the cost for running the system. And in an ideal system looks like this, that the more customers you have, the more you are paying. I mean, it's even more ideal if you would be paying less or so, but that's not realistic, right? And the curve should be linear. So that would be kind of ideal. If it's not linear, then at some point in time, you need to pay more for additional resources than you actually earn for additional customers. So then you would probably start avoiding additional customers, and that's probably not what the business would like to have. So in fact, that's one of the interesting metrics. So if you do analysis, then this curve is basically a good metric for most of our managers to show whether the new system, new infrastructure is basically fulfilling the demand they have. So the manager assigns an architect. The architect wants to build a cloud computing system now and put this into a cloud computing environment to make use of the scalability of the infrastructure and to implement its own elasticity. So when we have additional resources, we buy additional resources, we pay more money, but that's okay, right? So as long as it's linear. And in that case, okay, the management wants to avoid that the requirements are not fulfilled, the customers are not disappointed, they won't go away, and so on. So we have to have some definitions. Actually, it's pretty interesting that in this domain, the definitions are not so clear even. There are quite a bunch of papers. They all have contradicting definitions. So a pretty much standard definition is not so common, at least. So what we did to come up with a definition for the project was we did a literature survey among the most important papers, and we tried to find a common definition which captures most of the properties all the definitions had. And these are the results we came up with. So the first one is the scalability. So it's obviously an ability, so a potential to do something. It's in this case an ability of a cloud layer to increase the maximum workload it can handle as bounded by its SLOs by expanding its quality of consumed services. So what it describes is basically a relation between the workload on my incoming interfaces, so what's the demand to my own service, the amount of requests, if you like, and the amount of the complexity of the processing each request occurs. And that's in relation to the amount of resources I need from lower layer services. And lower layer services can now be either be thought of in a layered architecture style, so I'm using my business logic uses another business logic to fulfill its task. But it's also so that would be horizontal, but it's also in a vertical way. I mean, my business logic uses the CPU, for example, to compute its function. Yeah, and that is also a kind in the cloud world. That's a service, right? It's infrastructure as a service in a sense. Yeah, and now the essence of the definition says I'm scalable if and only if an increase in underlying resources, horizontally or vertically, also increases my capacity. Yeah? So if that's violated, then I'm actually not able anymore to scale, yeah? Because then I'm at a bound. Yeah? I could increase as more resources as I want underneath, it wouldn't change anything anymore. And every system has this bound. The question is just where it is. Yeah? Ultimately, they are where the unlimited resources are actually really not unlimited, but bound. So, elasticity is the degree a cloud layer can autonomously adapt the maximum workload it can handle as bounded by its SLOs to workload over time. Particularly interesting here in this definition we came up with is this bounded by its SLOs. So there's multiple definitions around which have a different wording there. We defined a service not to be compliant anymore if it violates any of its SLOs.
Why do we need to remember to remind the SLOs and elasticity? You have it already scalability.
Yes. I'm answering that in a second, okay? Efficiency, a measure that relates the demanded maximum workload a cloud layer can handle as bounded by its SLOs to consume services over time. So that's about the maximum workload and the amount of money I'm paying actually. So now back to Frank's question. Those sentences were the result out of the literature survey, yeah? By basically combining all the available definitions we found in, I think it was about 30 papers. Yeah? And now that was the outcome. Yeah? And obviously the observation is there are some common parts in here. Yeah? And this common part is actually this maximum workload the service can handle bounded by its SLOs. So it makes sense to give to extract them and give it a new definition, and that's basically what we call the capacity of the system. Yeah? So the capacity is the maximum work and load the system can handle. If we exceed the capacity, then obviously we will see congestion, and then all the service will break down. So it's an important measure to determine the capacity of our systems. Yeah? So that was one of the metrics we were most interested in the end of the project, to determine for any system its capacity.
So that service level objective.
Yeah.
If who puts this? If
The service
I put
level
it low, then I'm always 100% consumed, or then I can maximize much easier. If I put it high,
yes.
I may never reach it.
Yes. The service level objective usually is defined by the business demands. Yeah? So, for example, I mean, in our case, we often think about things like performance or reliability. There, we have typical measures available from user behavior, cognitive science, and so on. So, for example, if you think about a web request, most users in today's infrastructure world are not accepting any longer replies than half a second. Yeah? So that's then your SLO. And if you put it higher, okay, you can do that, but then you have a lot of unsatisfied customers, right? So it's basically it's not a real choice. Yeah? You have some limits in which you can play it, but it's not a real choice. Okay, so scalability now just is by replacing this capacity word. And now the question is, how can we measure those things? And we came up with some kind of metrics. Again, there's not so much standard metrics in literature to measure some of these properties. The capacity is measured basically in capacities of sub-metrics in a sense. So, for example, arrival rate capacity measures the maximum arrival rate. Arrival rate is the rate with which requests arrive at my service. The service is still able to handle without violating SLOs. But that requires a static work situation. Yeah? So we have to assume a fixed work. So all customers are at least doing the same kind of requests all the time on the average. If you have a changing work situation, you have a more dynamic system, then it doesn't make sense to have this metric. You need to define another one, which takes also this dynamic work situation into account. Scalability, we have defined the scalability range as an important metric, so that's basically the range in which our service is able to scale, so in which it can make use of additional resources. For elasticity, we have some metrics which are more from the outside of the system, like the time to quality repair. So the time to quality repair measures the time the system takes until it's fulfilling the SLOs again after violating them. Situation is, for example, think about a flash drop.
But typically you do the increase before you violate it.
Yeah.
Some prediction.
That's why I was giving you an example, right? So think about a flash drop situation, something you couldn't predict up front, right? So your bookshop is, we all would attack the bookshop, so to say, yeah, and come to it, and then obviously you can't react on this up front. If you can, yeah, then your mean time to quality repair is 0, that's ideal, right? If you can't, it takes now some time for the system to react on this new situation it couldn't predict, and that's the time it takes. And again, every system has both. Yeah? Every system has parts in which it can predict the behavior of the work and the load, and parts in which the work and load behave unpredictably, and you have to react to both. It can also be that you intentionally violate SLOs, depending on your business fees again. Yeah? So if penalties, for example, are low, or if the impact is low, then you might intentionally violate some SLOs, even if you could predict it. Yeah? But the prediction would lead you to run always on much more resources than you need for the normal case, right? So there's your decision field, right? So again, business decision in this. And the number of SLO violations, that's a complementary metric to this one. And efficiency, the consumer number cost, so this is the one which we saw on one of my initial slides, where we would plot the number of consumers to the operational cost, and this one is now a bad example, right? So if that's your situation, you don't want to have more customers. Good. Now, ultimately, these are the metrics we want to analyze. Yeah? So we would like to have tools which give us those metrics for system under design, under development, under re-engineering activities. Always also consider the last part. For that, we have defined in the project a method which basically you can follow, which is a little bit customizable, so you can skip parts, or you can use other parts, but in general it works like this. You have an existing service. We always assumed this re-engineering scenario much more than a definition of greenfield services, because greenfield services don't exist anymore in a large extent. Most of them are brownfield, because some existing IT system already did the job, but was not designed for this kind of scenario. So the first thing is you need to re-engineer your system. In our case, as we are dealing with models, we need to re-engineer into a model first. The model contains a model about what the users do with the system, so describing basically the load and the work situation the system faces. It contains a software model, in our case showing the services involved into the system, or the components, if you like, and how they are composed and how they interact with each other, which kind of requests they send to each other, and so on. And an infrastructure model. The infrastructure model contains information about the cloud, including also the ways to scale up and scale down, and so on. And when you have this model, you can run our tools to detect, first of all to analyze, then to detect, and finally to resolve all scalability/elasticity issues in your system on the model level. So you play what-if scenarios, basically. What if I would change my system at this point, doing something else, and then reanalyze it? So to finally to identify the target situation in a way that the target situation is known to work. Yeah, so that's the idea. As similar as the street example, yeah, where we use Sumo to look for the street to extend or for the street to build a new. If your system looks like ours, then it comes up with this result. So that's the result actually for this TPCW bookshop. You have a limit in scalability, basically meaning that you can only deal with a limited number of customers, and even before that, you will face increasing cost to customer ratio. Okay, so that's basically illustrating now what's happening next is in this analyze phase is, okay, for example, here we identify a number of users which use the system in which we find a bottleneck somewhere.
And it's always the database.
It's always the database,
Yeah.
exactly. That's a good
I
old
recognized already. Yeah.
That's the one I already learned in my studies.
Yeah.
This is what we do on Thursday.
Okay, good.
Yeah, but in fact, I mean, honestly, the storage part or the part where we have to deal with the data is obviously, or in most cases,
Well,
the
today we
critical
have
part.
eventual consistency.
Yeah, I mean, but that's also something you need to design for. Yeah, and again, another metric we didn't look at, for example, which is the maximum time to eventual consistency you would like to accept. Yeah. Okay, so here's the database. In this case, it's also a nice database. It can be scaled out, which not all databases are easy to do. In this case, we assume it can, and then it's not anymore the bottleneck. If you do the reanalysis, everything is fine now, and then we would implement ultimately this solution.
So what you get out of the analysis is that the bottleneck might be the database, and then you get hints which kind of database you need. Is that the mental model?
The hints you don't get, the rest was okay.
So you point to the individual components of
Yeah.
the application and say there might be a problem.
Yeah.
Okay.
Yeah.
But do you have some monitoring data, or you just look at the code?
Can I defer it for a second? I will go through my
Okay, yeah,
tools.
good.
Yeah.
Yeah.
But the answer is yes, we also have monitoring data. And the answer is yes, we also take code.
Yeah, okay. Yeah.
Yeah? So we take everything we can get, basically.
But you really assume that you have a database there which scales up?
No, that's just for the example. I mean, you can also have other types of services as long as you can model them. What the limits of the model are, we can discuss in
There
the
would be not the other way around. To what extent do you take into account, for example, continuously growing amount of data?
continuously growing amount of data is probably something we don't take into account. Yeah, I mean, it depends on whether you put it into this model or not.
Yeah.
You can put it in that model here, but then still it requires you some manual thinking when you apply the detection tools to figure this out.
Okay. And I can resolve your problem if I always over-provision resources.
Yeah, I mean, as long as, that only counts as long as your system is really scalable in all the resources.
Right.
Yeah? And often, for example, passive resources, like database logs or so on, might be the problem, and then you can provision as much as you want. Right? Yeah, it doesn't help. Okay, that's it. Just that you get an idea of the high-level outline of the cloud scale method. All these method steps are described each step in the book I showed you. So basically, you see these two types of routes you can take. The first question you have to answer is, what is your analysis based upon? Is it just on the model, which is applicable if you are really doing greenfield development, or if the code is way too complex to model, to analyze, and you want to really start with the model, or if you say, which were cases we had also in the past, that we are rewriting the system. That was the term yesterday, right? We are rewriting the system anyway. Yeah, so don't care about our old code, just build a model of our target architecture and so on. So then you go this route, you specify, basically this way is manually specifying the model, using the analyzer, getting the results done. This way is partially extracting existing code into a model and getting support from that. And this one is the other half, is if you have a system running and your target system is probably not so much different from the running system, you can analyze on code And the code analysis is working on static code analysis and on dynamic code analysis. So basically looking at the code, we had a discussion yesterday, so we are looking at object-oriented code only, but in an abstract way. So we don't care about the programming language, at least not at least in theory. And then in this code, we are looking for potential bottlenecks, and then we instrument the running system to figure out whether a potential bottleneck is a real bottleneck.
But would it apply if I have a bunch of microservices that do interact with each other? So what makes it determined to an object instead of it's a module and the modules to interact with each other?
I mean, what it makes special is basically the rules for reverse engineering. Yeah? So the rules for reverse engineering, they look at classes, interfaces, stuff like that. If you change those rules and you say, come on, I don't care, I have components, models, modules, microservices, OSGI classes, whatever, yeah, then you teach the system to work with that, fine too. Yeah? The problem is,
I wanted to start something.
yeah, no, that's a good question. The problem is just the effort. Yeah? The effort for the reverse engineering tool. And this is a huge effort.
Is the system flexible enough so that you are metadata driven and saying, okay, it's an object or a component?
Half-half, I would say, depending on who wrote the part of the system. Some parts you can exchange, and some parts you can model your own rules for detection. In some other parts, for example, the extractor here, this is really hardbound to an OMG meta model, which is called KDM, Knowledge Discovery Meta Model, and the rules for converting this into our model, they are hard-coded. Because they were so complex that we had to hard code them, and also it was running them on industry systems was in the beginning, when we had it more flexible, way too slow. Because these models are so large, I mean, we took like, what was it, 500,000 up to 1 million lines of code. That gives you a very huge model that already loads about a quarter of an hour, and then it's just loading, not analyzing it, right? And then when you start analyzing it and it takes days, then it's not of any use. Yeah? So there we had to hard code it just to speed these things up. Yes. Okay, and then everything was made available in this Cloud Scale IDE. I don't want to show this one to you because I wasn't able to install it. The tools which we have developed, I mean, this is a nice UI which we developed for the EU project. It is not maintained anymore, so therefore it's not so easy to run it on a modern macOS, for example. But I have most of the tools also in our Palladio tool, which is kind of the background tool for this whole thing. And there everything is still maintained and most of the stuff is still running, so I can show you the stuff there. It just doesn't look so nice. Okay. Given the time, I'm skipping this part here of the calibration of the model. And I just want to go into the detectors, and the rest I'm showing you. So I just want to show you a little bit about how we detect problems. Maybe that's an interesting area. So the idea of detecting problems was to use the metaphor of a doctor. Yeah? So when you go to your doctor, you basically explain the doctor your symptoms. Yeah? So you would say, okay, my knee is hurting, and then you would ask, okay, what did you do? Did you play tennis yesterday? Something like that, yeah? A multitude of questions, and then in the end there comes the diagnosis.
I don't say anything.
I was just not looking intentionally at you. Yeah? So that's the idea we follow here too. So the idea is we are looking for typical symptoms systems can show when they are not scalable. Yeah? And there is a bunch of known anti-patterns systems you can observe on systems which show you problems like this. So for example, traffic jam, I mean that's the one which is easy to explain. You saw it on my slides, right? So this is when requests start queuing somewhere in your system, and the queue gets longer and longer and longer, and requests take longer to be processed, or hiccups.
This can be detected based on code analysis?
No, that's okay. That's the detection is a combination of both, right?
I would have been shocked, yeah.
In the code, we detect potentials for it, and then we confirm it or disconfirm it while running the system.
Did you use it based on code smells, for example? How do you do it?
No, we didn't use code smells because code smells are often coined for maintainability, but we use rules which are similar to code smells, which lead to those anti-patterns. Okay, I will show you one in a second. Yeah, and then the result is as similar as to the doctor. Yeah, you will say, okay, okay, you have those, you show those symptoms, then you're
absolutely lost a friend.
Your diagnosis is database.
We can talk about consulting.
Okay, yeah, and this is done in 2 steps. In the first step, we look at the code. For example, this one here is an anti-pattern in the code for scalability, the so-called one-lane bridge. One, or could also be n-lane bridge. Yeah, the n-lane bridge is basically a piece of the code where the concurrency is limited to n. And that obviously limits your overall scalability or processing capabilities. Now the question is, okay, which code could cause such a one-lane bridge? Yeah? And now you need to think of code patterns or custom code patterns which result in these kind of problems. One easy one is this one. Yeah, that's a piece of Java code. That's a typical one-lane bridge. You have a piece of synchronized code. Yeah? So that's the classical instance of the one-lane bridge in Java, where you can execute this do process just with one thread and therefore limit the parallelism. Yeah. So and when you know such patterns, you can teach our tool to detect them. In our case, I mean, this is now a piece of the model we have extracted. Here you see, back probably not. It says acquire action. Acquire action is basically the behavior for getting a lock, and somewhere else there is a release action. Yeah, so the whole block in between is guarded by a lock and therefore a potential n-lane bridge. And that's detected by our tool. When you run it, here you see on this TPCW example we used, there's quite a bunch of those synchronized methods where these Java locks have been used to protect some internal data structures for concurrent modification, and that was basically limiting most of the parallel processing already.
Can you go one slide back, please? What has this to do with the database? We don't do synchronization, we do it automatically, right? We do it internally. This is not database.
It was not offending you. Yeah, the example. You mean the example with this guy saying database congestion?
Well, he does not know how to program.
But that example was not database suggestion. Yeah. So that's basically really not a problem of the database, but a problem of the business logic in this system. Yeah? So it's not always the database,
No,
but
it's a business
it can also. I mean, the typical sources are, besides the database, bad written code in the business logic or wrong configuration of the VM.
Yeah.
So these are the stuff we typically detect.
And robot thread pooling?
Yeah, I mean that's part of VM.
Okay, that was.
I was summarizing it there. Okay, yeah, and now when you have found those potentials, you need to confirm them. Sometimes you have these problems in the code, but if nobody uses the code, then okay, the code is still kind of okay. So we need to have measurements from the running system, and there, this is such an expert system. Basically, it guides through its detection by a multitude of questions where you always say, okay, this symptom is there, this symptom is not there. If it's there, then the set of potential problems is limited by those which show that symptom. For example, here, if the response time raise over time, that's an indicator, for example, for traffic jam or for ramp up. If it's not the case, then you have some other problems. Or maybe you don't have any problem if none of the detection rules applies. So for example, if you go here, response time is raising, but the CPU utilization is staying low, which means, okay, obviously it's not raising because the CPU is doing a lot of work, but because something is waiting. Yeah? And then we come to our one language over there, which is our synchronized statement, because then everything is waiting in front of this monitor, this Java monitor, and not processing further. Here's an excerpt of the whole.
Wait, so during runtime, with the monitoring data to detect, there must be a one language. But you don't point to the code. This is the monitoring data.
This is based on monitoring data. If you run the spotter up front, as I showed you, then it specifically looks for this one.
So and it monitoring first, and then you do the code analysis?
No, code analysis first. You see the static, you see, for example, the synchronized block.
Yes.
Then you instrument exactly this block.
So my
and now you inspect this block, whether this block shows this behavior.
Got it. I thought that your tool recommends to fix the code first, and then
no.
Okay.
That's all analysis part. Yeah. So it really, it's just about getting you to the problems.
Okay.
So this is one way of running it, right? And then you know for sure. You can also run this tool standalone, then you get the problems, and it might not be pointing you directly to your problem, but only to the region in your system, right? Where the problem is.
But usually it's a much more complex way to get to one language.
Yes, sure. I mean, we had in the realistic systems, we had discovered also one languages and other things, and still, in most cases, it's not so easy to explain why. Yeah? Even if you did upfront code analysis, even if you did the whole thing, then still, in the end, you just have an area in your system where the problem is, and still manual end analysis needs to be done, but at least it's guided, right? So at least you have already some idea what to look for and where. Okay, so then you have this problem hierarchy. You see there's some, here's database logs again, only for you. And in the tool it looks like this, so you see the whole hierarchy and how and at runtime it moves through this. Moving is a bit relative because it can take days or weeks depending on your system. But then you see, okay, which symptoms have been detected, which have been not detected, and you see how it's actually investigating your system for those problems. Good, and then you can analyze the system, but I want to show that part on the tool because of time. So I have, I have built a system here. What's the time? 10 minutes left. So I start with the analyzer part, and then if you have questions, we can also have a look at the reverse engineering, but the reverse engineering was already on the slide, so I'm skipping that for a second. This is more like the engineering part, so where you build the model of your system. This one is a very simple system, again, just for demonstration purposes. My famous Sunshine to Go, that's the one I use in tutorials like this. It's basically a weather app or weather web service where you can query the service for the weather in the next 10 days at a specific location. So in Crete, this would be easy. You should always say sun and 20 degrees or something. But otherwise, it's not so easy. And for this system, I have made some interesting architectural alternatives here. So this is the front-end service, taking the request basically and diverting it. And here's the database with all the weather data in it. Yeah, and as an alternative, you can also have a cache in between. Now, this is a cache component, and the cache component's behavior is for our models is simple because you can just say, okay, with a certain probability, the queried region is in the cache, and then we don't do query the database. If not, then we need to query the database and infer additional demand. And the database here, according to my slideware, is also configured to scale in and out. This is done via so-called architectural templates, a technique one of my PhD students has developed, which makes the modeling easy. You just apply things similar to UML stereotypes. In this case, you see here one of these stereotypes in which you specify just the main important attributes of that behavior. In this case, this is a replicable component. The component replicates, it starts with one replica, so one instance. It replicates, or it scales out when the response times of its answers are above 5, and it scales in when they are below 1. So, autoscaler rules basically. Yeah, and the last one just specifies that it is responding to responses it gives. Yeah.
So is this a Palladio model?
Yes, a Palladio model.
Are you trained in this in any way?
This is modeled by manually now.
It's a static model.
It's not static because it knows how to do this scale in, scale out actions. So in that case, it's actually a model of a dynamic architecture, but a static model of a dynamic architecture. Yeah. It's not modified itself. Yeah.
But it's read-only, right? The database is read-only.
The database here is read-only, yeah, so it can be scaled.
That's the easy part.
Yeah, yeah.
Yeah.
But it's a demo.
Yeah, okay.
I only have an hour.
Can I follow?
Sure.
This is the performance model of a real system, right?
Of a real demo system, yeah.
Of a real system. And I have specific resources with specific characteristics. Are these parameters of this model?
Yes.
But these are things that I don't have to get from experiments. I know these things, what type of CPU I have, how much memory I have, these types of things, right?
Yeah, either you know them, or if you don't know them, you either need to query them or do experiments to figure them out. Yeah? So this whole model needs to be calibrated. And the calibration step here for that model, because that's something I can't show, and I could talk another hour about, this is the most critical part of the whole approach, and also the most complex one, I would say. Today, people are calibrating models using machine learning techniques and stuff like that, which eases the task a lot, but still requires some thinking, I would say. Yeah.
And this is used primarily for initial deployment?
The typical use cases are greenfield development and deployment, where you don't know upfront what your system will look like exactly, or you have different alternatives to evaluate. And the other one is where you start on a brownfield and you further evolve your system. Yeah? So adding new functionality or migrating the system, modernizing the system, things like that, where most people come up with those questions. So the typical question the customer has, right? If I'm changing my system in that and that area, will it still perform as before?
Are you using this to give you specific prediction results, such as how many nodes should I deploy on to have a certain type of response time for this application?
That's something you could get out of it.
Okay.
Yeah, so in particular over time, yeah, you could see how much nodes you have over time depending on your work and load situation. So then from that you can also compute your cost and so on. So for that system I can show you the results because I did them in the morning, and then we can discuss a little bit about what we see. So I plotted them here. So explanation is on the x-axis you see the simulation running over time. So this is just time increasing. On the y-axis we see the response time of the system itself. 5 would be here, so this is where the autoscaler would kick in. SLO I didn't define here, yeah, so we can think of an SLO somewhere in this range. And now I did 3 experiments. Let's look at the green one first. So the green one is one where I basically overloaded the database intentionally. Yeah? When I'm overloading the database in the first place, then here at 5 the autoscaler kicks in and it deploys a new instance. At 10 we are still not fine, so probably we create another instance, and then we see at some point the effects of the new instances taking over the load, and the situation gets better. Down here, we are below this 1 second threshold, so we are releasing instances again, and then obviously it leads to the fact that we were facing problems again, and then we are buying resources again. So that's the kind of situation which usually remains undetected or hard to resolve in practice, yeah, because this is a kind of an oscillation of your autoscaler rules. That's a question also people would like to answer: are my autoscaling rules somehow stable in my environment? In this case, it wouldn't be stable. That's the way. That's actually the situation where the cache was deactivated. So I basically didn't put the cache into my system. The other ones are now the ones where I played a little bit with my cache. So the blue one is the so it's not so easy to see, but it actually didn't reconfigure at all. That's the situation where the cache answers to half of the requests. So then I was trying to figure out, okay, where is this kind of borderline? So if I cache half of the requests, then I'm fine. If I'm caching no requests, I'm getting into an oscillating state. So somewhere in between there might be a steady state, and that's what I was looking for. And that's actually the red curve. This is where the 30% of the requests are cached and 70% of the requests are answered from the database. And actually what we see here is sometimes it reconfigures a little bit here and there, but just one instance, not just 3-4 instances at a time, and then releasing them again way more than needed and so on. So this red system would be one which would actually operate nicely in this situation. So a combination of a certain cache with a certain cache coherence and a replicable database gives you a good engineering situation here, and that's how I would configure my system now, right? So now I implement it and I configure my autoscaler rules according to these things. And figuring this out without a model is probably something difficult. Yeah? So you need a lot of measurements. You need to instrument. You need to deploy your system a lot of times, doing different types of analysis and so on. Actually, our experience shows that in practice, most people end up having something which is at least in danger of the green curve, because they just deploy autoscaling with standard settings of the autoscaler rules without thinking about their work and load situation, and then, yeah, they might run into trouble because the green curve is actually fine in the sense that it eventually fulfills its SLOs all the time, but the SLOs violations over time or the time to repair might not be good enough. Yeah? So the time to repair here is probably the first violation. If you take this 5, it's from 20 seconds to 60 seconds, so it takes 40 seconds in which the users will see inappropriate response times, and that might already be not good enough, even if the system is elastic, even if the system is scalable, probably not what was wanted here.
And this does already consider provisioning time. How long does it take to provision an instance?
Here the provisioning time is 0. You can model the provisioning time. You can also model the provisioning overhead it causes on the machine which does evaluate the reconfiguration. Yeah. Here, I didn't do that. It's a simple model, but you could. Okay, so then I close my talk just with an outlook to what's not so easy to do still. There are also some pieces there. Areas in which the system showed problems in the industrial evaluation, I would say, is the model extraction is still very problematic. So the models you get out of realistic systems are tremendously complex, even if simplified a lot, and hard to understand and deal with. Yeah? So if you take only code or measurements to create your model, without doing manual interaction, this is probably still, at least still until today, not working good enough in a way that it would be useful. So in the end, if you're not treating your model as black box and just playing around with the parts which you can, when the model is black box, you probably need to at least spend some time to create at least some smaller pieces of the model manually and then maybe fill them automatically via machine learning or things like that. We need more of those architectural templates. So we have lots of cloud scaling, of cloud patterns there, scale in, scale out, types of architectures, 3 layers, and so on. However, when you look at microservices and so on, you often see things like asynchronous communication over message buses and so on. And actually, maybe in the future we change our statement, like the database is always to blame. Yeah, these days the message bus is always to blame. And in SOA we had this situation already, I think, in the past. Yeah, in our current projects, the message bus is the problem in most of the cases, not the databases, but the message bus. And therefore, we need more precise models of message buses actually to detect those problems in there better, which we don't have at the moment, but which we are working on currently. Yeah, I think that's the most important two pieces of open issues in our current project.
Okay, thanks a lot. So, do we have much?
Message buses are using the projects.
The tools I see most at the moment is RabbitMQ and SwiftMQ. And Swift.
Okay.
And the good thing is we already know some of the anti-patterns. Yeah, we could teach our detecting rules those tools have. And the bad thing is when you try to figure out why they are failing, you start reading the documentation of those systems and they are awful. And sometimes it's really crazy what people write about the system. No way of getting any insights how to configure the system correctly for any situation. It's a mess.
Even the others using those systems, which they don't understand.
Yeah, I mean the ones using don't understand, but also I would consider myself to be an expert, so I should understand the description of what they are doing. No chance. I mean, I don't get it. It's a weird mix of business logic, description of consistency levels, of locking statements and stuff like that, which contradict each other. And obviously, you know the code is probably not doing this, what's been described, and even the description is so high level that sometimes you don't get what's the real behavior. So would be an interesting thing to see, to really analyze the system and compare it to its description, whether there's any overlap at all. Yeah? Whether the description says something, but the behavior in the message bus is actually completely different. I could imagine this.
Okay, here's another question.
Just one comment, I guess, is Palladium assumes you know your components, what components you have in your system. In case of a black box system, probably that wouldn't be an approach you can follow, right? And then you would need something more statistical and another kind of modeling. And also, I think the reactive way of scaling doesn't do very well if your measure of latency is in the tails, 9.9. The more you go into these very strict latencies, the more you need predictive abilities.
Yeah.
Right?
So predictive ability is one thing which is also on our future work agenda. I mean, creating means so that you can model the reaction on the model level in a predictive way. That's something PhD is currently working on. And the other one, yes. I mean, that's a core assumption that you at least have a kind of a gray box model. So a pure black box model doesn't give you much insights in your system.
So for me, it would be very interesting to learn what it means to make your approach feasible for data services in the context of big data. So, but then you usually need to have different kinds of databases there working together, and then you need to orchestrate and do that things, and then it gets much more complex to find the one lane or the bottleneck or something. And then you need to learn how the system behaves under certain topologies of databases and to be predictive in order to control them.
That's why there are two pieces, right? So on the one side, we have those spotters. I mean, they are not connected to Palladium in any sense, right? So they are analyzing code or measurements directly. You can use them also standalone. There's no need to Palladium. The other side is the modeling part, right? Yeah, and I would say, okay, the detection part is probably hard to connect to the modeling part because of all those little nasty details where things can go wrong.
Okay, and Thursday morning we will talk about the data thing there, and possibly after that we can talk about how to bring these things together also. If there are no more questions, then we will now have a break, and we proceed at 4:30. Thank you again.